Hello, this is Math 2270 coming to you from the College of DuPage for summer 2020, and this is the conclusion of the lecture entitled Qualitative and Numerical Approaches. So we talked about qualitative approaches. We spent a lot of the term talking about analytical approaches, but a differential equation can possess a solution and we may not be able to obtain it analytically. So to round out the picture of different kinds of analysis we can do, we're going to discuss solving them numerically. And so what we use is the differential equation as the cornerstone of an algorithm that approximates the unknown solution. This discussion spans 9.1 through 9.4 in the Classic 5th edition and is the subject of two problems on the take-home component of the final exam. So we talked in the qualitative section about the direction field or the slope field. So suppose you have that. Then what you can say is, okay, so we used y prime equal f of xy to generate that. So we have the slope at all of these points in that grid. We also have an initial value that y at x0 is equal to y0. Now here is kind of what's happening then. So we have to go through the point 2, 4, and so we have to follow that. So this is what we got qualitatively. And you know that the solution curve and the line are very close to each other if there's not a very big difference here. I mean, when the delta h, or when the h, I guess, is small, that's true. Okay, so let's talk about how this goes forward then. So we basically have this tangent line, and then we take a step, and the step can be very small, but it's h. So I will go from x0 to x1, which is x0 plus h. So I'm taking steps of h. Now at h, that gives me x1, so this is x1, y1, but this is along the line. So you see it really does not match up with the solution at that point. But this is where what I say is, but now we have to adjust the slope. We don't continue going this way. We're adjusting the slope and we figure out what is the slope up here, and we take the next step. And so you see this was the differential equation that we had, the initial value problem. So how we get x1 is here. Then we have y1, but now we're going to use the different slope, and we're going to use the slope at this new point. So we continue in this manner. We end up with a recursive relationship where we can get y1, y2, y3, dot, 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 can be defined recursively by this formula. Yn plus 1 is equal to yn plus h, h was your step size, times f of x in, y in, which of course is your slope. And x in is always going to be x0 plus n times h. This is called Euler's method. And the reason tangent lines is in quotes is because even though this is a tangent line, we're not really doing a tangent to the curve anymore. The tangent of the curve is up here, so we're just modeling the slope. So that's why there are quotes there. Here's an example. So you consider the initial value problem. Y prime is equal to all this. It's very nonlinear. Y of 2 equal 4. And we're saying we want to obtain an approximation of y at the point 2.5 using h equals 0.1 and then h equals 0.05. Okay, so we start here. So when x is 2, y is 4. But then we use the recursion relationship that we have here. We find out that y1 is equal to, and that's going to be 4 plus h in this case is 0.01. And then this is going to be, I substitute y0, that's going to be 0.01. Square root of 4 plus 0.4, and the 2 is squared. I do that calculation, I get 418. So you see, then when we take the next step, we went to, this is what the new value of x is, and that's what we got for that. But now that we have y2, we can find y3. And we can find y3, or we can find y2 this way, and we can find y3, and so on and so forth using this recursion relationship. Now, if we did this with h equals 0.05, the steps are lower, well, the steps are smaller. You would hope it would be more accurate, but you see you get a table like this. So these are the kind of tables where you will test your software later. That really is section 9.1. You should read the examples there and check your software with it. With Euler's method, we can gain accuracy by decreasing the step size, but this also increases the number of calculations, and there is error that happens. The improved Euler method, the Huynh method, attempts to address this by averaging the slopes of 2 consecutive steps, and should, I put that in quotes, do a better job of tracking most solutions. It really depends on how poorly behaved the function is. Okay, so how does that work? Well, it works in this way. So his recursion relationship in the improved Euler is going to be yn plus 1 is equal to yn plus, but now we're using the average of the nth step and the n plus first step, the slopes, divided by 2, because we're taking the average. And that is supposed to make you think it's going to be a better fit, and of course we take this times h, where that is the step size. Now we have a little bit of a problem though, because you've got yn plus 1 here and yn plus 1 here, and that means that is implicitly defined. But we know that yn plus 1 we can use as approximation Euler's formula, and we call this yn plus h f of t n comma yn. So you see, we can write that in a little bit simplified form this way. So you see, we can also use this recursion relationship without that problem of that being recursively defined. That's 9.2. And again, there's examples there. You should make sure that you follow the examples. Another approach is called the three-term Taylor method. And if you start thinking about it, the Taylor series starts looking, you start with a y, then you have a derivative, then you have a second derivative, so on and so forth, and you have different powers of h. So what you're doing here is you're going to use three terms rather. And so you're going to say the recursion is yn plus 1 is equal to yn plus yn prime times h. And by the way, that really is just Euler's formula. But then you add yn double prime times h squared over 2. You know what h is, so that's not a problem. And you might say, where do I get y sub n double prime? Well, you get that because y prime is equal to f of xy. So if you take the derivative of both sides, you have y double prime. So that enables you to use this, and that was 9.3. 9.4 is the last section that we're doing, and this is called the fourth order Runge-Kutta method. And here they do even more of a weighted average of the slopes at different points in the interval. And you see you've got 1, 2, 3, 4, 5, 6 is the total weight, so you do a weighted average there. But these k factors are, you start with k n1 is going to be f of tn yn. But you have to figure out k sub n1 first, and then you can figure out what k n2 is. And once you know what k n2 is, you can figure out what k n3 is. And once you know what k n3 is, you can figure out what k n4 is. And that, after you have all of those things, then you can get yn plus 1. So there's a lot of calculation here, and you should remember that for n equal 2, 3, and 4, each k sub nj depends on the previous term, k nj minus 1. Okay, I used to go to computer labs and set the students about doing this. They worked in groups, helped each other, and it really was a very good session. Can't do that now, so here's my recommendation. You should use Excel, MATLAB, C++, Python, I almost don't care, to program these 4 approaches. To test that your software works, you can validate your software using the examples that are in your Classic 5th edition textbook. You should be able to match those results. And then once you've tested and validated your software, you can run your software on the take-home final exam problems. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.